So we'll discuss following observation. Suppose that X is union of a collection of path connected open sets alphas, each of which is each of which contains the base point x naught and x. First, the homomorphisms G alpha from pi 1 to alpha to pi 1 x induced by induced by inclusion a alpha into x, they extend to a unique homomorphism phi from star alpha pi 1 a alpha to pi 1 x. Right, so this we already know, right? So if we consider a collection of homomorphisms, right, from J alpha from here to here, then there exists a unique homomorphism phi from here to here, such that, so this is not required, right? So that is why we are saying that they extend, right? They extend, right? So this pi 1 alpha, so basically we said that this is satisfies following property that J alpha composed this phi sorry so we have seen that if we denote these inclusion maps of this, so there is because this pi 1 a alpha is a subgroup of this free product, right? So we can inclusion map be denoted by I alpha, then this is basically equal to J alpha, right? But if because we are considering pi 1 a alpha, right, as a subgroup of this, so in place of this we can write as P restricted over pi 1 alpha a alpha to be equal to J alpha. This next, if I alpha beta from pi 1 a alpha intersection a beta to pi 1 a alpha, this is the homomorphism, induced by the inclusion a alpha intersection a beta a alpha, then we have I alpha beta composed J alpha equal to J beta composed I beta alpha. So again, I alpha beta is from here to here. So I beta alpha will be from pi 1 a alpha intersection a beta to pi 1 a beta. This one. So you just see here how it comes. So this inclusion, we have two a alpha intersection a beta. Okay. There is an inclusion from here to a alpha, and there is an inclusion from here to x. Okay, and a alpha intersection a beta to a beta, and there is an inclusion from here to x, right? So composition of this inclusion and this inclusion equal to composition of this inclusion and this inclusion. So suppose this composition, right, if we denote it by psi, right, then psi star, right, will be psi star will be what? Psi star will be from pi 1 a alpha intersection a beta to pi 1 x, right? So psi star will be from pi 1 a alpha intersection a beta to pi 1 x. Okay. Now psi star will be composition of this homomorphism induced by this inclusion composed with the homomorphism induced by this inclusion. So homomorphism induced by this inclusion, we have just said it is I alpha beta, and this one it is J alpha, right? And now similarly this will be equal to this will be equal to homomorphism induced by this inclusion. So that is I beta alpha composed this one j beta, right? It means that these two are equal. The kernel of phi contains all the elements. So we are not saying exactly what are the elements of kernel of phi. So what is phi? We have just seen that phi is a homomorphism induced by those j alphas from pi 1 a alpha to pi 1 x, right? So the kernel of phi contains all the elements of the form I alpha beta omega I beta alpha omega inverse. For omega in pi 1 a alpha intersection a beta. So how this comes, just see. So we are not saying exactly what the kernel of, exactly what are the elements of kernel phi. We are saying that these elements definitely will be there in the kernel phi, right? What will be the other elements? We are not saying anything about that here. So how this they will be there? We just see that if we apply phi over this I alpha beta omega I beta alpha omega inverse, then just see that I alpha beta, so here, right? So I alpha beta will be I alpha beta omega. So the phi is a homomorphism. So we can write like this I alpha beta omega and then phi I beta alpha omega inverse, right? Now I alpha beta omega is where? I alpha beta omega is going to be in, you see here, this omega is an element of this. I alpha beta omega will be in pi 1 a alpha, right? Now phi applied over pi 1 a alpha, right, will be what? So this one you can write as, so this I alpha beta omega is an element of this, and phi applied over this will be what? Basically phi restricted, this is what phi restricted over pi 1 a alpha applied over I alpha beta omega. And similarly here phi restricted over I beta alpha will be an element of, will be from here to pi 1 a beta. So this is will be an element of pi 1 a beta. So this applied over this will be nothing but pi restriction of phi over pi 1 a beta applied over I beta alpha omega inverse this. And from here, you just see, we have seen that from previous observation that this phi is actually extension of these J alphas, right? So this restricted over pi 1 A alpha is nothing but J alpha, right? So J alpha, this is nothing but J alpha composed I alpha beta into omega, and this is what? This is J beta composed I beta alpha omega inverse. Now J from here I alpha beta composed J alpha equal to I beta alpha composed J beta. So these two are equal, and hence this you can write as because so in place of this we can write this one. So this is J alpha composed I beta, and because this is a homomorphism, so this times omega into J alpha composed I beta into omega inverse, right? So omega and then J alpha composed I. This is alpha. This is I alpha beta. This is I alpha beta again, and this is omega inverse because this is equal to this. This is equal to this, so here this will be replaced by this. So this is J alpha composed I beta alpha beta omega to omega inverse, and this is J alpha composed I alpha beta. So this is identity, right? And this is what? Identity, right? It means phi applied over this is identity, means this belongs to the kernel of phi. So let us write statement of Van Kampen theorem. The full name is Seifert-Van Kampen theorem. Van Kampen theorem. It says following: if X is the union of path connected open sets A alpha, each containing the base point x naught in X, and if each intersection A alpha A beta, right, is path connected, then the homomorphism phi from alpha pi 1 e alpha to pi 1 x is surjective, is surjective. If in addition, right? So other than this much, if uh, some more conditions are satisfied, what are those conditions? If in addition each intersection A alpha intersection A beta intersection A gamma is path connected, this is path connected, then so intersection of any three of these A alphas, right? If so, here condition was intersection of any two of these A alphas is path connected. Here there is something more. So this is path connected. Then the kernel of phi is the normal subgroup. So you know that if you have a homomorphism, then kernel of the homomorphism is of course the normal subgroup of the original domain group. So of course the kernel will have to be a normal subgroup. Then the kernel of phi is the normal subgroup generated normal subgroup n generated by all the elements of the form I alpha beta omega I beta alpha omega inverse uh, where omega belongs to this, of course. So we have already discussed that, so we will not write again. So where omega belongs to pi 1 A alpha intersection A beta. So similarly, you have to choose all the different A alpha and beta, right? And choose elements of this kind. And so phi induces an isomorphism X, right, between A alpha quotiented by n. So phi induces an isomorphism between pi 1 x and this, because uh, n is normal, n is kernel of that phi. So of course, if you have a homomorphism from G to G1 to G2, if f is surjective, then you know that this is epimorphism, right? Surjective homomorphism. Then G1 quotiented by kernel F is isomorphic to G2, right? So we will see next some applications. So first example, so let us consider this, right? Figure 8. So basically, or you can say that there are two circles, right? This is one circle, this is another circle, and they intersect at a single point, right? So we can make two circles, right? Intersect single point. So suppose this point is x naught, right? So whole space is x, right? So x is this is space. Suppose we consider, so we want to, we know that a fundamental group of a circle is Z, right? So we want to compute fundamental group of this, right? So you can say that this is figure 8, figure 8. How we are going to do it? We will use C for this Van Kampen theorem. So if this S1 and S2 both are open sets, right? Open subsets of this X, then means we can directly use. But X, yeah, this you see this if this is S1, this is S1. So this S1 is not an open subset of X, right? You can see that because if you take any open disk containing this one, this copy, then it will contain some portion of this also. So of course, S1 is not an open subset of X. So what we are going to do, so we'll just consider this A. Suppose this is a point A, this is another point B. Okay, so put U equal to X minus A and V equal to X minus B, right? So clearly, clearly U union V equal to U union V equal to X. U and V are open subsets of X, right? So they are not open subsets of, suppose we are considering this in R2. So they are not open subsets of R2, but they are open subsets of X. So it is up to you. You verify it, right? So try to find open sets in R2 whose intersection with X is U, and try to find another open subset in R2 whose intersection with X is V, right? And uh, also U intersection V is path connected. So these are actually path connected open sets. Connected. So you just see that what is U? Basically, U is your just this one, and then just one point removed. What is V, right? So U is path connected, it is open. What is V? So V is this, right? Just one point removed from here. So these are open. Their intersection is what? Their intersection is something like this, right? One point removed and then something like this. Okay. Now it is clear that this one u intersection v, which is this one, this deformation retracts to a point, right? You can slowly and slowly you can shrink it. Deformation retracts to this point. So this x naught. And this one deformation retracts to this circle. Okay. So this x naught, x naught. And this one deformation retracts to this circle. You can slowly and slowly you can shrink it. So I will just clearly u intersection v deformation retracts to x naught. U deformation retracts to a circle S1. V deformation retracts to another copy of S1, right? Now, hence, pi 1 u equal to pi 1 S1, because if u deformation retracts to S1, then fundamental group of u and S1 will be same. So this is Z. Similarly, pi 1 V equal to pi 1 S1 equal to Z, right? And pi 1 u intersection V, because if deformation retracts to a point whose fundamental group will be pi 1 x naught equal to 0. Now we can use Van Kampen theorem here. So Van Kampen theorem says that this pi 1 u, all the conditions for Van Kampen theorem to be applied are satisfied. So pi 1 star pi 1 u star pi 1 v will be isomorphic to this pi 1 x quotiented by n, right? Where n is normal subgroup generated by those I alpha beta omega, I beta alpha omega inverse, right? So n is generated by these kind of elements, but omega is from where? Omega is from this pi 1 a alpha intersection a beta, right? So a alpha and a beta are what? They are u and v. There are no other components, right? So this belongs to u intersection v, right? But pi 1 u intersection v is trivial, right? So it means omega also will be trivial, and this is what? This is simply 0, right? The trivial element. So all the elements of this form will be trivial. It means n will be a trivial group. It means this is nothing but this, right? So this will be isomorphic to this, but this is pi 1 u is what? It is Z, right? So zero. Hence, this pi 1 x is isomorphic to Z star Z, right? Pi 1 u is Z, pi 1 v is Z. So it is, this is isomorphic to Z star Z, right? So this is fundamental group of this figure 8 is the free group generated by two elements. So Z star Z is what? It is free group generated by two elements. So we stop here today. We will see some more applications.